What are categories of thought you can use to develop a concept image? When constructing a concept image, I can think of at least 7 different categories of ideas that provide unique paradigms through which to view each mathematical concept definition we study. Verbal descriptions. Formal concept images are written in highly technical jargon that may seem foreign upon first examination. When creating verbal descriptions to encode a concept definition, we must complete 2 related but identical tasks. Independent tasks, not identical tasks. First, we must be able to summarize the concept definition in our own words entirely and completely. This process requires us to decode each technical word or phrase we encounter, create or access mental maps of each underlying idea, encode these ideas in words that make sense to us, and synthesize a description of the concept definition that is entirely in our own words. In doing so, we must be sure to address possible inaccuracies with our encoding and to ensure that we have not lost any important information. The process of encoding a concept definition in our own language fully and completely is by far the hardest and most important part of creating a verbal description of a concept definition. However, if we plan on being a part of a community of working professionals who use these ideas, it is also important that we learn to use the technical jargon associated with the concept definition correctly. In other words, the second task of creating a verbal description is to learn how to use technical terms correctly and to encode our understanding in the language of the field. Secondly, we have visual descriptions. Many concept definitions can be effectively encoded using meaningful visuals. Such visuals include but are not limited to graphs, images, diagrams, or maps that help encode and interpret an idea geometrically or visually. Often, when constructing a verbal description, it is useful to create an associated visual description with labels, comments, and explicit connections between the words we choose and a corresponding diagram we create. Thirdly, we have symbolic descriptions. Concept definitions in mathematics are also encoded using symbols and notation. There are 2 types of symbolic representations that might be helpful for us to refine our concept images. First, there is a notation that others have created for us and that we decide to adopt. When studying mathematics in college, it is often wise to use the standard notation that our professor introduces. As an expert in the field, our instructor might have made many choices about notation that will help us avoid confusion without communicating to us why she made those choices. Unless we have a very compelling reason not to, we might choose to adopt the notation our professor uses and ask for clarification about why our teacher made these choices for notation during office hours. On the other hand, there are some instances that we will want to create notation, such as variables, symbols, operations, etc., for ourselves, in case we need to be more careful to communicate the implied meaning of our notation to a person that grades our work. The fourth category is algorithmic descriptions for pen and paper analysis. Many concept definitions in mathematics are related to specific algorithmic or procedural processes to find a specific result or execute a specific calculation. In order to fortify a given concept image, we will find it very useful to analyze algorithms and procedures that relate to a specific set of concept definitions. Logic descriptions. Concept definitions in mathematics are often encoded using formal logical structures such as conditional statements, universal quantifiers, or existential quantifiers. The process of creating robust concept images often involves a detailed analysis of the logical structures implicitly stated in the concept definition. Modeling descriptions. One of the most beautiful and frustrating dimensions of mathematical theory is the formal concept definitions are often abstracted away from the most powerful applications in which they arise. When encoding a concept definition, we can create nuanced meaning and deep understanding by identifying the idea with applied modeling scenarios in which the idea arises. This type of identification and integration empowers us to make connections between specific mathematical objects and lived experiences that we observe in our daily life. By doing so, we can start to make connections between our non-math classes, our career interests, and the formal theory we learn in our math classes. This type of encoding can lead to much higher levels of motivation and an intuitive grasp of a concept definition within a framework that interests us. Such knowledge can lead to concept images that are very sticky and form a bridge between our formal education, our social life, and our future career plans. This knowledge can also help us to get paid. Lastly, algorithmic descriptions for digital computation. A professional applied mathematician living in the 21st century who expects to be paid to solve problems using mathematics not only develops concept images with knowledge from the 6 categories described above, but she also needs to build special knowledge of how to use digital computers to solve applied problems. This often requires specialized knowledge of computation, data encodings, and algorithms that are specifically designed to converge on finite computation machines.